All right, here we go. So last time we were talking about the Mount Kilimanjaro data, which I obtained from a friend of mine who I ran with in college in cross country and track back at CSU, and this is like in the 80s, the 1980s. What else would it be, right? So I actually ran into him like 20 years later, and we started talking, and we ended up, collaborating on this project and getting a paper out on it involving high altitude sickness and medications that people take that they may or may not take for, treating altitude sickness. And so there's a lot of good data here, very interesting data set, a really big data set. And the way that we looked at it last time is we put in random effects, up to quadratic random effects. And you can show, we've talked about how if you put in random effects, you induce correlation, right, on the covariance structure for Y. So even if you have a simple R structure, like, and this was a quiz question as well, or related to it, if you put in a random intercept, we induce the compound symmetric structure for the covariance of Y, which is good. That's good that it accounts for repeated measures, but the issue is for longitudinal data that may be too simplistic, because what you're doing is you're assuming, regardless of the distance between the time points that you have the same correlation. And so it's much better than nothing. If you have correlated data, or even longitudinal data specifically, having a random intercept is much better than having nothing, even if it's oversimplified. But if you have higher order random effects, so if we have like a random intercept plus a random slope, that does better in terms of modeling time-sensitive repeated measures. And even further, if you have a quadratic, that helps even more. So just by having these random effects, we do a better job at modeling repeated measures over time. But one of the questions is, can we do better if we additionally add like a AR1 structure or something that's even more time sensitive? So that's what we'll talk about today. What we saw last time is we had a model fit, and we had a non-positive definite G matrix. And the reason why that occurred is because we had a zero on the diagonal, essentially. And so the question is, if you get something like that, is that a problem? If you have a non-positive definite G. And we talked about how it may not be a problem, because what you're ultimately interested in is V, or the covariance matrix of the responses. Because G is just one piece of it. Remember that we have, actually I'm gonna open up my Word, because I'll be able to write on it a little bit easier. So give me just a second to get that. Okay, so I'll just decrease the size just a hair on this. So this may be one of the most important formulas for this class, and you guys already know it, is the ZGZ transpose plus R. That's, if I had to pick, if you said what's the most important formula for this class, this might be it, because this tells us how we model the correlation of the data in a mixed model. And it shows you that we combine random effects and the error covariance structure in order to do that. And so if you have a G matrix that's, and you guys can see my screen, right? All right. So if you have random effects, you take ZG, Z transpose, and then you add in what you have for R, and you get, you're kind of like a chef. You're baking, and you're adding a little bit of this and a little bit of that, And so you can have a combination of things that will give you a V matrix. And even if you have a simple, like if you have sigma squared I for R, you can have random effects. And if you have up to quadratic random effects, you can actually do an okay job modeling repeated measures over time, even though the random effects essentially are put in to account for, between subject variability, or to account for other nuisance factors that we may have in our data, usually. That's usually why we have them in there. And they may be of more interest in that, but there's different types of random effects we can add to the model. But my point being is that we have different ways of modeling repeated measures. And you can do it through adding random effects or specifying the error covariance structure, or both. Elise, yeah.
Matt, when you're in SAS and you do a random intercept, are you saying that that's altering the ZGZ piece of the equation as opposed to R?
Yes. Yeah, and it also shows you that you are, just by adding random effects, you're affecting the covariance structure for the responses, even if you have a simple R structure. Back to the Mount Kilimanjaro data, you may be okay, even if the G matrix is not positive definite. If you have, and we talked about this, but if you have issues with the Hessian matrix, or obviously if the model doesn't converge or things like that, those are big problems. But having a non-positive definite G may not necessarily be a problem. We also did see in the random effects solutions that we had zeros for standard errors for the intercept and for the slope. And so we really can't do inference for that. So we have some issues. If we're really interested in doing subject level inference, then we're limited in that. But usually, like I said, like random effects, mainly we're trying to deal with variability that we're not necessarily interested in, but we know is there and we need to account for it. For these data, the most important thing I want is that the fixed effect estimates for the relationship between oxygen saturation and altitude. Those are the most important things. And then we can also say some things about the quadratic random effects and whether they're significantly different than the population average with this particular model. If we wanted to do more on the subject level inference and make more statements, then we'd have to keep finding a model that would work for us. So we're going to keep looking at this data set.
Quick question.
Yeah.
If your G matrix isn't positive definite, does the software find like a near positive definite matrix, or does it just use it the way it is? Because I know you can approximate a positive definite matrix.
So what you can do, it'll just say the best thing that we could find is, didn't allow, is essentially zero for that element. What you could do, you can specify boundaries for parameters. So you could say, well, I want it to be at least this amount. And so it can search within that space to find what the best parameter estimate would be based on the constraints that you put in. That'd be one possible way to do it. Okay. So naturally, like the variances should be positive, right? And that's a normal constraint that's added to the model. You can actually remove that and sometimes you'll get negative variances that will optimize the model, which don't make much sense. And that's why that boundary is usually placed in the search, so the variances are positive, correlations are between -1 and 1, so there's already some boundaries placed in the model, but you can play with that if you want.
Okay.
So you guys, I think, probably know this is kind of more of a review page, and you guys may be okay. Like if we had 4 measures, is this something we should go through, or do you want to jump this? Any strong feelings?
I'd like to review this personally.
Okay, we'll do it, and it shouldn't take too much time. So if we have 4 measures, then our R structure is going to be 4 by 4, right? So we have, you're going to have 4 rows and 4 columns. And so you're looking for, the matrix represents all possible combinations of measures that you have. So like this element here would be the first time point and the last time point. You have a covariance for that, right? So for the simple structure, that's just the identity matrix. And so you're going to have zeros off diagonal. And all of these, I'm just for time, I'm just going to say symmetric. So I'll just do the lower diagonal and they're symmetric matrices. But we also have this element we can pull out, it's like my lamp. It's like, it has a brain to it and it knows it knows it's messing with me. I don't think you can leave that one. No, you can. Okay. Sometimes if it keeps disappearing, you just have to start over, but okay, I will win this battle. Okay, so that's the simple structure. The CS structure, there's a few different ways you can write this. If you're thinking about, you know, I like the random intercept approach for this. You can actually specify and I guess I probably will since that's the way we have it. But I'm going to write it as if I added a random intercept instead because I like the idea of having within and between subject variability. So make a note of that. But this would have down the diagonal we'd have these elements, and then in the off diagonal we have just the sigma b squared. Okay, so this formulation is, I think you get the point. So this would be, I'll just say random intercept type formulation. Okay, and the thing is, what makes this nice and intuitive is that if you change this, like we have covariance structures, so R is a covariance structure, but there's also a correlation version of that. So like in SAS, if you ask for R, you get this covariance matrix. So it's in terms of covariances and variances. If you standardize this to the correlation matrix, you can get that by asking for R core. And it's essentially for any element in there, it's dividing by the standard deviation of so like for this element here, it would divide by the standard deviation the square root of the corresponding variance in that column and that row, right? And so you'd end up with ones down the diagonal. And then in the off diagonal, they would be, what would the elements be in that?
Would those be the ICC?
Exactly. Yep. So it would be the interclass correlation. So that's kind of why I like this formulation. The parameters actually might look a little different if you actually just specify R to have the structure and you don't add a random intercept. But it would the underlying model is the same, whether you do the random intercept approach or directly model the CS on the error covariance structure. The unstructure is the most flexible structure we have in modeling repeated measures. So the thing is, if you add the unstructure in the R matrix, then you're not going to get anything more by adding random effects. Okay, so if you do the unstructure, you don't need to add random intercept for subject or anything like that. In terms of how flexible you can model the repeated measures. And for 4 time points, you have unique variances down the diagonal. And then you have any correlation of interest in the off diagonal. So you have a very flexible model here. One thing that I've done in the past, you get different information from the R matrix and the R correlation matrix, and both are useful. So sometimes what I do is actually, I'll put in the R correlation matrix, because that way the off diagonal elements are standardized and they make more sense. But since that matrix has 1 down the diagonal, that doesn't really give us any useful information. So sometimes what I do is actually put the variances down the diagonal, and then I put the correlations in the off diagonal. But if you do that, you just have to clearly state that this is a mixture of those 2 different matrices. But that's kind of a useful way to present the information. The AR1, as we know, I can pull out the residual variance, and then down the diagonal we have between 2 time points you have phi, and then phi squared and phi cubed as you increase by that difference by 1 going down, and then so again, these are all symmetric. So obviously, the AR1 is going to work if you have equally spaced time points. And if you don't, there's a couple of things you can do. You can either go to the spatial power structure or some kind of spatial structure, or you can actually trick the code and use the AR1 by putting in extra rows in your data set and putting in missing values for Y. Okay, so that you get the right gaps between the time points. So for example, if you have a study where you're collecting data on the weekdays but not the weekends, you can add in the weekend days and just put in a missing value for Y to account for the gap, so that by the time that you start measuring again the next Monday, that you've accounted for that space that you have on the weekends. The spatial power, let's just have an example. Let's say we have days 1, 2, 3, and 6, kind of like we had on our quiz, right? Then we'd see, for that, we'd see can give myself a lot of space here, but in the exponent, the element's going to look like this. It's going to be, I'll say JK. So this D is accounting for the distance we have, and this is related to element JK in the matrix. Okay, so J row, K column. And so you have to tell it what that metric is. So when you're actually running this, you have to tell it what is that time variable of interest that's going to account for the spacing. And so if we have if D is representing days, and these are the days, then you just use the gap between those. So the 1, 2 element, there's a gap of 1. So we would have phi there, and then for the 1, 3 element, there's a gap of 2. So we had phi squared. Between elements 1 and 4, there's a gap of 5. So we'd have 5 as the power there. I'm going to fight you on this one. Phi squared. No, that would just be actually just phi there, right? And then the next one would be phi squared and phi. Does that look right? So we're accounting for, so the decay, you know, you have phi and then you have phi squared, and then it's gonna go down a lot more because it's accounting for that extra space that we have there, right? There's many others, but those are really the ones I use the most. You know, there's the toplets. There's actually in SAS there's a lot of different spatial power structures you can use, but this is the one that I use the most as a spatial power. It's the other name for this one is continuous AR1, and that's the name that R uses. It's the CAR1 structure, but it's comparable to what SAS calls spatial power. Any other questions on those structures? So that's probably a, you know, kind of a review for you guys. I noticed on the quiz, like I asked a question about, you know, we have these, I think it was months, but it was the same numbers. It was 1, 2, 3, and 6. And I said, what do you do? Like, what would you think of the random intercept, and how could you do that better? And most said spatial power. So it sounds like you guys had learned that in 6612, or maybe you read ahead. And like a lot of you said spatial power, I was surprised. Like there's other options. Like we've learned the unstructure, and the unstructure would work too. And I was accepting of those because I didn't know if maybe I talked about it. I don't remember if I talked about it, but a lot of people said spatial power. And
it was in homework 3.
What's that?
It was in homework 3, and I think that's why.
Oh, okay. Okay, good. That's good that you guys got that. But you know, you could have also said, and some people did, like the unstructure is another way you could deal with that unequal spacing. So either one's acceptable, and there's other answers too that you could have. But
I have a question, Matt.
yeah.
When you specify a random intercept and the covariance pattern, so is your random intercept being implemented in your G matrix, and your covariance pattern is in your R matrix? Is that correct?
Yeah. What I'm talking about here is the R structure directly. Yeah.
Sure, but the random intercept would be in the G matrix. Is that correct?
Yep.
So then where would the normal variance covariance of the model parameters, what matrix does that lie in? So if you're looking for like the normal covariance matrix that you would get from a normal linear regression that has your.
So I think are you talking about for the fixed effect estimates? Yeah, so that'd be the covariance of beta hat.
Beta hat.
Right? And that's a separate thing.
So when we write out our statistical models, we don't normally include that matrix.
You know, you can, and we actually did talk about it a little bit. And you guys, I had a homework question as well, right? Where you guys had to derive the variance of beta hat.
Right.
So you guys actually did that, I think, for a full rank model. But that's important too. And I think that actually comes out, like for R, that comes out as default output in R.
Right.
Yeah, so that could be useful as well. But that's a separate thing from what we're talking about. We're talking about the variance Y, the variance covariance of Y, and then what are the pieces that go into modeling that?
Okay.
Yeah, good question.
One more question.
Yeah.
So if you specify both the random intercept and the UN, aren't we over-parameterizing the model? Does that look like over-parameterization?
Yeah, it really is. I mean, the model may still fit, it may still work, but in terms of modeling the repeated measures, yeah, you're adding more than you need to by doing the unstructure for R and then adding like a random intercept for subjects. Then yeah, I would say that you're over parameterizing it. And again, it may not be a deal breaker. You may actually get a model fit through it. But once you add the unstructure, you've saturated that modeling the repeated measures, right? So do you know what I mean by when I say saturating? Like we can think of that in terms of modeling the covariance structure or in terms of modeling the fixed effects. You know, this question came up. Well, I think I talked about it. In terms of the fixed effects, how do you saturate the fixed effects if you have group and time? Well, the way you do that is by having group and time as class variables and then adding the interaction. That's the most flexible modeling of the fixed effects that you can have, right? In a similar vein, when you add the unstructure for R, you've saturated how you can model the repeated measures. That's as flexible as you can get, and you don't get anything more by adding like a random intercept, or you know, if your goal is to model the repeated measures. And so we use the unstructure a lot for if you have a limited number of time points. But obviously, if you have, you know, once you get, you know, above 4, like 5, 6, 7, then you're introducing a lot of parameters into the model. And that's why the unstructure works pretty well for, you know, 2, 3, 4, 5. But once you go beyond that, you really start increasing the number of parameters, and it's probably not going to be an efficient way to model the data. So yeah, Benjamin, good question.
I have a question.
Yeah, Carrie.
Maybe it's a request. Last semester, he was pretty much saying that like usually you either specify the G side or you specify the R side, but you have to have pretty good justification to specify both. And so as you go through examples, if you could just like talk through why you're choosing one of the sides, that would be really helpful because that's still
okay
for me.
Yeah, that's a good question.
Thanks.
You know, and what we're going to talk about today, like this is like the key stuff we're getting into now, is a situation where we're including both. And I think the reason typically why I include both is because really I'm looking at modeling the repeated measures. You know, I'm interested in the covariance structure for Y, and I want to get the best structure possible. And by adding both the repeated and random, I'm dropping the AIC. It's clearly helping the model to have both in there. And so, like, you know, I talked about being a chef earlier. It's like, you know, I'm trying to add a little bit of this, a little bit of that, but my goal is to model the repeated measures the best way I can. And especially when I have large data sets like this one, we have like almost 14,000 or between 13 and 14,000 observations. And so I'm not concerned that I'm over parameterizing the model. Obviously, if you're adding stuff and it's not helping that much, then, you know, I agree that, you know, a lot of statisticians would say, go with the simpler model if you can. And I would tend to agree with that. But in cases where it's clearly helping you to have both the repeated and random, and your main goal is to focus on the variance for Y, you know, you're just trying to get that best structure, then, you know, I don't see why you know, any downside to adding both. I can tell you on a practical side that SAS does pretty well modeling both. R, it does well, like if you just add in random terms, you know, that the LME4, I think the LME4 package is pretty good. And if you're just adding random effects, that does pretty well. If you're just modeling the R structure, what's the function you typically use for that?
The GLS function.
GLS, which is generalized least squares, right? And actually in the course notes, if you want to read about that, specifically what that is, the methods for that, I lay that out. We don't get into that. I'm not going to spend time in a lecture talking about that. But the GLS function, I think that works pretty well if you're just specifying the R matrix. In R, you would probably use the LME function in the NLME package if you add both. But I haven't been as confident in R when that's like, it works sometimes and other times it doesn't work too well. And I don't know if that impacts what people tell you, like you should go with one or the other, but typically not both. If that's a reasoning, you know, if they're, but for me, for the more complicated models, I'm probably going to use SAS until R can figure out a way to include both, have a good package that will be able to model both. So like the data I'm talking about today, I would do this in SAS. I probably wouldn't do it in R. And I know R is, you know, it's in academics really use this data set, and R is changing all the time. So I'm guessing before long that there'll probably be, you know, hopefully some packages available that will do better in modeling both the R matrix and the G matrix. So before we get to get back to the Mount Kilimanjaro data set, I want to talk about the direct product Kronecker structure. And this is applicable if you have repeated measures over 2 dimensions. So for example, if we're measuring, let's say, leg strength on subjects over 3 time points, and we're measuring strength on both the left and the right leg. So we have, you know, you would expect correlation if you're taking measures within the same subject at 2 different places. And then, you know, for repeated measures, that's the other dimension. So we have repeated measures over space and over time. And we can use a direct product Kronecker structure. So you either call it direct product structure or Kronecker structure to account for those doubly repeated measures. And so if we have 2, you know, the measurement on each leg and then at the 3 time points, then our covariance structure is going to be a 6 by 6 in this case. And so, so this here would be, you know, another way to write this would be for the left leg, we're going to have measurement, and we have associated variance for that. That actually was good. It helped me that time because I wrote an R up there instead of what I wanted, which was a square. So my pen actually helped me this time, didn't fight me. And then we have the other leg, and then we have the covariance between it. So it's the same thing as what I wrote, but just if you want to, you know, think of it in terms of right and left legs. And then for time, so for day 1, 2, and 3, day 1, 2, and 3. So for each dimension, we create an R structure, and then you take the Kronecker product of that, and you end up with something that looks like this. Okay, so for, you know, for the left leg, for the right leg, and then the between the right and the left legs, you have those pieces that go into this Kronecker product. Okay, so this would be the left leg, this would be the right, this would be the left and the right. So in the diagonal, you have the covariance matrix that's related to the left leg, and then the lower right, you have the covariance matrix related to the right leg, and then the off diagonal would be the covariance between the left and the right, but that's also time sensitive, right? So this would be time 1, 2, and 3, time 1, 2, and 3. So you end up with it looks fairly complicated, but you still, it's pretty manageable because you have a limited number of parameters that you're using. It's actually 4 parameters that you're using. And one of them falls out. The sigma squared epsilon will fall out because it's redundant. We don't need that extra parameter. And by taking it out, all of the parameters now are identifiable and estimable. Okay, so another example, measuring cortisol 3 times a day for 7 days in a row. So let's say we have day 1, 2, 3, and we take measurements in the morning, noon, and evening on each of those days. So we actually have 2 levels of time involved in our study. How would you think the AR1 structure would work for these data? If you were to take measurements, like in terms of correlation, how do you think the AR1 structure would work here?
If we didn't use the continuous AR1, it would treat the difference from like noon to evening on the first day as the same distance as evening on the first day to morning on the second day.
Yeah, that's right. So that's the issue we talked about, that the AR1 is good for equally spaced observations. Let's say that we are able to kind of get them roughly equally spaced from each other, or that's not really a major issue for these data. What's another potential problem with the AR1 here?
I think if you have missing time points, then you have the same issue.
Okay, that's true.
Because if we have 2 structure, both of them are AR1, we can, when we product them together, they could be like just the 1 parameter over there, other than use 2 parameters separately. Is that what you mean?
Okay, Randy, I like some of what you're saying, like you have 2 structures. And so what you started saying there was along the lines of what I'm looking for, actually. What's the benefit of actually using 2 structures here rather than just 1 structure?
Because we can get a more accurate structure over there.
Yeah.
But if we use the AR1, we can just use 1 parameter with 1 covariance structure to describe all the things other than 2 parameters.
We could use just 1, but think about like the correlation. So if we use the AR1 here, so if we're considering between morning and noon, the correlation would be phi. Between morning and evening, it'd be phi squared, right? Between morning and the next morning, it'd be phi cubed. Why might that not be so great?
Because maybe mornings are nested within days.
Mornings.
Yeah, well, maybe I said that incorrectly, but it seems like your time points are nested within your days. So it wouldn't make sense to look at one morning to the next morning.
That's not quite like, I thought the way you're going to start was what I'm looking for. That actually is an important point that you're bringing up, but not what I'm looking for in this specific case. What you're talking about, the nesting and crossing, that's a good point. We'll talk about that more next week. But what do you know about like your behavior? Go ahead, Elise.
We know cortisol is higher in the morning, so your morning measurements are going to be more correlated to each other than your evening to your morning.
Yeah, that's what I'm looking for, is that even though these 2 are further apart, like this morning to this morning, this could be have a higher correlation, right? Compared to morning let's say morning to noontime, or morning to evening within a day, right? So I'll say could have. So you could actually see a stronger correlation between morning to morning than, let's say, morning to evening, even though the time is further. And so if you just use the regular AR1, you're forcing that decay, and you're forcing the morning to the next morning to be lower than the morning to evening within the same day. And so I think you'd probably at least want to try a structure where you have, so for R, for day, you could do, the problem with SAS, it's kind of limited in what you could do, but let's try the unstructured here. So we have a variance for the morning, variance for noon, variance for evening, and then the covariances between those, because we don't know exactly if there's something simpler that might work. But let's use that for within a day. And then actually, so I'll say time within day. So that's like the general time, morning, noon, evening. And then for days, then, the first day, second day, third day, and so forth. Let's say if we have 4 days, then we'll use the AR1. So we have that sigma squared epsilon, and then it's our usual AR1. And that'll be better, like, especially if we have a lot of days. I'm just writing 4 because, it's easier, but we might have, let's say, 20 days in a row. And for that, it's definitely more efficient to use the AR1. So this way, we can test and see if that morning to morning is stronger than the within a day, morning to evening, or something like that. That gives us the flexibility to model that. So again, the thing that we're trying to do ultimately is model the variance of Y, or covariance of Y. I use those interchangeably, but that's that matrix that tells you about the correlation between repeated measures. And there's a mixture of ways you can do it. Random effects or R, defined structures. And so today, with getting back to the Mount Kilimanjaro data, that's a big data set. It's pretty complicated. And this is one where actually adding both makes sense. So this shows you what the data look like. So what happens is these subjects are climbing Mount Kilimanjaro, and they're actually camping. Like, it requires like 4 or 5 days to go from the bottom, from the base camp, all the way to the top. I think typically they camp like 3 or 4 times. So on their way up, they're climbing, and on day 1, we get an oxygen saturation measurement in the AM, and then another one in the PM. So there's actually 2 measurements per day. And so day 1, we have 2 records, day 2, we have 2 records, and so forth. And you'll notice that the altitude is actually the same for the PM measurement on day 1 as it is for the AM measurement on day 2, and that's because they're at a camp. So they go to a camp, they take the measurements, they sleep, they wake up the next day, take more measurements, and then they hike, and then they keep doing that process. So for this first subject, we have 17 records, so we had 17 measurements over time, and you can see the day, there's actually 8 days, and typically we take 2 measurements per day. And we also, we're measuring X's altitude, and we have a column to indicate whether they're taking the Diamox treatment or not during the climb to help prevent altitude sickness. So that's what the data look like. And so that'll kind of motivate why we model the data a certain way or not. Approach 1 is what we already talked about, what I showed you last time, where we have random effects, and this is up to cubic, not cubic, quadratic, up to quadratic random effects. And then this just a simple R structure. So we're just modeling through random effects. And we end up with the correlation parameter between 2 errors that's 0.08. That doesn't make sense if we just have a simple, so let me, I'm not sure about that one, why I have that in there. I don't think we have, see what I set up here is we use a simple R structure. So I don't know, I'm gonna cross that one out here. I don't think that applies in this case. But it's a reasonable approach because we have up to quadratic random effects. We're modeling repeated measures over time pretty well. And this is the AIC we get. Approach 2, why don't we try adding an AR1 to see if we can get anything more in modeling the repeated measures. So we still have up to the quadratic random effects, but I'm adding an AR1 structure for R. It's kind of an approximate approach because of the fact that they're not exactly equally spaced. We have AM and PM, AM and PM. You know, if they were if it was 7 o'clock AM, 7 PM, 7 AM, 7 PM, they would be equally spaced, but I don't know if that's the case. So it's an approximate approach. And the way that we do that modeling is I do it on rec number, okay, which is this variable here, which is just the record number. I'm not sure why it skipped 2 there, but that's just an indicator for the order of the repeated measures that we're taking. And by adding that AR1 structure, we do see a 54-point drop from our original AIC. And how would you see if that's important? Well, the AIC builds in a penalty, right, for the number of parameters that you have. So you can compare head to head, and it's a drop. So you could say that just by comparing AICs as a lower AIC, we get a benefit from adding the AR1. You could also do a test. Do you guys know what test you could do in this case?
Likelihood ratio test?
Yeah, so you could do a likelihood ratio test and compare nested models. You know, you essentially can compare the log likelihood values, and that difference is approximately has a chi-square distribution. And so the degrees of freedom would be the difference between those 2 models. You know, you have nested models. I think you would see that it would be significant with 54-point drop. And just the addition of how many are we adding? How many parameters are we adding? With that AR1. Well, how many parameters does the AR1 structure have?
2.
Has 2. That's right.
So
But yeah, go ahead. Somebody gonna.
I was just gonna say we're adding 1 because we're adding
Exactly.
row.
We're adding, yeah, exactly, because we have the simple structure that already has sigma squared epsilon, right? So if we specify the AR1 structure, it has 2, but it only has 1 more than the simple structure. So we're just adding 1 parameter. and we get a drop of 54. So it seems like it helps to add the AR1. Based on what we've talked about, do you have any other ideas for modeling the repeated measures over time?
Can you talk about what you're modeling as an unstructured type in the code? It looks like you're specifying unstructured for something.
Yeah, that's a really good question. And I'll answer this one, and then you can answer my question after that. So the G matrix, there's essentially two types of G matrices that we're concerned about. One is the unstructured, and one is the variance components. And the difference is one allows covariances in between the random effects that you have, and the other one doesn't. It just has zeros in the off diagonal. So for the G matrix, you're typically going to specify either an unstructured or variance components. If you don't say anything, it'll do the variance components. So for the unstructured, and this is a really good question, by the way. I'm glad you asked it. The unstructured, you'd have a variance for the intercept. You'd have a variance for the linear term, and you'd have a variance for the quadratic term, and then you'd have all of the possible covariances between those. So that's the unstructured. If you didn't say that, then the way that it would model that G matrix would be like that, and these are both symmetric. It would just set the covariances to 0. Why is the unstructured helpful here?
So it's you're not assuming independence between subjects?
Between those specific terms, the intercept and linear terms, or the intercept and quadratic. So for example, for example, let's say that if you increase the intercept, you tend to increase the slope as well at the same time, then that would be a covariance between the intercept and the slope.
Right. But aren't you specifying the subject as your random intercept in where subject equals ID?
Why did I do that?
Right.
Or what was the question?
Isn't the subject equals ID part saying that your random intercept is the subject?
No, that's for all of those terms. It's for the intercept and the altitude, and which is what we're looking at, and altitude squared.
Okay.
So that would apply to all three of those.
Okay.
Would you ever not want to specify type equals unstructured for your random intercept?
Sure. If you find out that those covariances are pretty weak, and if it looks like there's not much of a relationship between the intercept and the slope for altitude and the quadratic term for altitude, then and you can compare it, right? You can rerun this and look at the AIC to see how much of a benefit we're getting by modeling the covariances between those terms. So you could test that out. The other thing I can tell you is by adding the unstructured, that gives us the ability to model the repeated measures even better when we have those extra parameters in there. Now it's true that we also have the AR1, so we're doing modeling the repeated measures over time or over altitude in a couple of ways by having these more complicated random effects, as well as specifying you know, the AR1 structure in this case for R. Yeah, again, if you don't say anything though, it's going to be the variance components structure. Okay, so going back to my question to you guys, any other thoughts on modeling these repeated measures over the changing altitudes or the changing times? There's one that we, yeah, go ahead.
Would you specify the AM PM column within the day for your
Yeah.
covariance pattern?
Yeah, so well, yeah, I think you're at least touching on something that I'm looking for, which is what we talked about today, which is a Kronecker product, right? There's actually two elements of time in our data. We have day, and then we have time within day, kind of like the data we just talked about, right? So we have, instead of morning, noon, evening, we just have AM and PM. But we can use that same principle where we have, you know, maybe the mornings are more correlated with each other than the morning to evening within the same day. And so by doing the Kronecker product, we can model these two types of time in the same matrix. And this is what the code would look like. It looks really complicated. It's mainly because I added a bunch of estimate statements here. The actual model and the random and repeated statements are just this top part right here. So, if I add repeated, and then the first element is the time within a day, that's the AM, PM. And then the second element was the larger unit of time, which is day. And I specified the unstructure for AM and PM, and that works well, right? Because it's only a 2 by 2. You have the first element being the AM, the second element being the PM. And then for day, we have a lot of days. And so the AR1 works well because there's only, well, there's 2 total, but one of those, you know, the sigma squared epsilon will actually fall out. It becomes redundant in that Kronecker product structure. So we have a pretty efficient way of modeling repeated measures and also accounting for those 2 types of time that we have. And I still have the same random effects up to cubic in that model. So
in the Kronecker product case, when you specify an unstructured covariance pattern, you're not making the random intercept redundant?
No.
Okay.
As long as you like, it's possible that we may get a 0 estimate in that G matrix again, but it's not making it redundant like I mentioned before, where if you take a Kronecker product of 2 covariance structures, sometimes one element will fall out because it becomes redundant. And this intercept, this is different. Remember, this is in G, whereas the Kronecker product is going to show up through R. And that approach that I just talked about is actually approach 5. So we talked about 1, 2, and 5. I added a couple more in there that weren't very good. If you just have an AR1 structure and you don't have random effects, the AIC actually goes up a lot. The one that I just talked about with the Kronecker product plus the up to quadratic random effects, that has the lowest AIC. So actually we improved the model by accounting for the AM/PM measurement within a day as well as repeated measures across days. You get the best covariance structure. one of the key things is if you're going to compare these AICs, you have to make sure that you're comparing a model that uses the same number of observations and why your outcome is the same between those models.
They actually have to be the same observations, don't they?
They have to be the same observations. Yeah,
Not
they
just
have to be the same
number.
observations. Yeah, so really, yeah, you're right. So this would be the same records. So you can cross that out. It should be the same records. But I assess that by I can, if I see that the n is the same, then I'm assuming that we're actually using the same records as well.
I have a question. If you have a random intercept on the random side on the G side, and then you specify whatever R matrix you want, if you did this current like multi-dimension R side, can you still interpret the ICC as normal, or is that like null and void if you specify something on the R side?
You can compare. Yeah, you can do any comparison you want as long as you have the same model. You're basing your model on the same records, and the outcome is the same. You can do comparisons, between models that only specify G versus those that specify R versus those that combine both of them. Is that your question?
Can you do like ICC, interclass correlation? Can you still do that? Like, is that still a valid to look at if you specify stuff?
Oh, I see what you're asking. I think you have to be careful. It could be conditional. It could be a little bit different, and so you have to make sure that the ICC, like you can get an ICC out of it, but it may not be apples to apples if you start modifying, the R structure. So you just have to keep that in mind.
So that's really a random intercept model thing.
It really is. Like, I think it's cleaner. Yeah, if you're going to be doing ICC, typically you do that, for like random effect models, and you could have higher level ICCs, like for nested models, it still may be appropriate. So you may have more than just between and within subject variance. But yeah, you typically see that for random effect models. I'll just make a quick mention on the last number of slides here. I talk about how you can model two different outcomes using a mixed model, even if they're completely different, just by considering them as repeated measures. And we're kind of, I don't want to start getting into this because we're pretty much out of time, but in a nutshell, what I did was I took two different outcomes. One was FEV1, which is a lung function measure, and another, which is distance walked. And the units are completely different. And the way I did this was I created a new variable y, and I considered these as two repeated measures. And by adding a variable called type, which refers to the type of outcome, and including interactions between type and every other predictor in the model, I can actually, I think of it as tricking the mixed model into creating a joint model, a joint outcome model. But really, we're doing it by including this type predictor, and then allowing I'm using a canonical product structure here where I have type of outcome as one dimension of the repeated measures, and then visit, which is the repeated measures over time. And so I'll let you guys read those slides, but I just wanted to at least mention the gist of what those slides are about. Okay, so I'll let you guys read those. So in our toolkit, we have, you guys are pretty comfortable with adding random effects. And I think you're also comfortable with specifying the error covariance matrix. And really what we're talking about today is that you're not limited into one or the other. You can do both. And I think it's true that there's an advantage to simpler models, but especially if you have a data set with an ample sample size, you may get benefits by adding both random and repeated statements. That's kind of SAS talk there, but specifying random effects as well as an error covariance structure, there's nothing that says that you have to just use one or the other. Carrie's question was a good one. Like as we keep walking forward, we can think about why we would, in cases where we would want to add both rather than one, or one or the other. There's different things to keep in mind, and it's not just AIC. It should be more than AIC, but that's one of the things that we can use to figure out if we can, if we should go to a more complex model. So I think that's pretty much we're out of time. I'm going to hang around. I'm going to get off, but we can talk about the quiz and any other questions you guys might have. Keep looking for some data for your project, and eventually I'll get a new homework up for you guys. But I figured you probably wouldn't mind a short break from homework. So just keep enjoying the outdoors and thinking about some data you can use for your project. And I'll be back in about 10 minutes.